Hi everyone, my name is Cliff Preston. I work with the mine monitoring team along with HxGN radar and Hexagon mining. And so today what I want to present to you is about our mine monitoring program and slope monitoring in open pit mines. This is something that we've been doing for the better part of a decade, and I have a lot of neat data to show you and how landslides transform and how we can use that in open pit mining to optimize our production and optimize safety and these types of things. So I'll start with an overview of the business and what we do. So it really comes down to, let's see, oh, wrong button. Monitoring systems solutions that we have, as well as the customer service and services that we provide with those monitoring solutions, and then the integrated software that kind of brings it all together. So we really sit in the middle of this little circle here, where we provide all these services to the mines. And the reason that we do that is because to have a successful monitoring program, you really need the hardware, the software, and the service behind it to make it a success. So what do we do? Well, we're the #1 technology leader when it comes to mine monitoring. We provide the highest end technology to the end users. We operate over 550 radars in the world across 210 open pit mines, and we have 20 or more than 20 now service centers worldwide to maintain this. And just to give you an idea of the companies that we work with, we pretty much work with most major mining companies at this point, running these programs all over the world, really. Probably many of you familiar with mining know that these are a lot of the mining countries that have a lot of mines. So what does this entail? Well, on the far left-hand side, you see we have the HxGN radar products. These are the slope monitoring radars. We have several different types, and I'll go through what those different types of radars are. And then we also bring in the Leica sensors like the total stations and GNSS devices. And then we bring that all together inside of our Hexagon Geomonitoring Hub suite that you can see here. This integrates the data between all these different sensors. And then we also have some hazard monitoring equipment. That's a Doppler style radar. This runs through a software called GeoCloud. And then at the end, we bring it all together with services and support. And I'll talk more about those services and support later, but the services support is multiple layers depending on the needs of the mine site and the local staff that they have available as well. All right, so within the mine monitoring team, we have, again, 24/7 remote data monitoring. So this is live monitoring. It's always collecting data. It's always real time of showing what's happening in the mine. We have over 70 staff that are working on this, working with mine sites, delivering this data. And really what it's about is to collect this data, set thresholds, and be able to alert and know about the changing conditions that are happening there as you're mining. Yeah, go ahead here. So here's the monitoring applications that we really focus on. The first is background long-term monitoring. A lot of times we use total stations for this. This solution gives us, that 3D displacement data at long ranges. Of course, you can only really measure at long ranges where you can put prisms. So we usually consider this for long-term monitoring because we know that it's surveyed in, we know exactly how much movement is happening, and we can continue this long-term campaigns for many, many years within the mines. But we can't see everywhere with the total stations because there's a lot of inaccessible places in the mine that we want to know about. And that's really where the radars come in. The radars, of course, we don't need to place any sensors on the slopes themselves. They can just take these measurements all over the mine 24/7. And that's really our next step up is to provide the radars. So you can see some images here. We have the IBIS FM Evo and the IBIS ArcSAR Performance here. These are the two main types of radars that are being used in open pit mines. And I'll show you kind of what the data looks like from those and explain those a little deeper. But the main advantage or the main benefit of using a radar in a mine is that you can go really long ranges and cover very broad areas, as you can see in this image here. This pit wall is about 3,000 meters away from the radar itself, and at that distance, we expect to have an accuracy of around 1 millimeter. So it's extremely accurate at long ranges, and it covers very fast areas. And additionally, it does update this map about every 2 minutes as well. So it scans every single one of those pixels every 2 minutes. So when you think about back on the earlier slide, I showed you that we have more than 500 radars in the world running right now. They're generating somewhere around 5 terabytes of data every day. Another application that we use the radars for, and we primarily use the IBIS FM Evo and the TM50 to monitor tailings dams. That's because tailings dams don't usually have a lot of movement associated with them. We expect them to be relatively stable. And so we use products where we have a long baseline and we can see very small changes over time. This has been a quite successful campaign in monitoring many different tailings dams around the world. There's many active right now that are being measured. And it's just another great application to see how things are changing and if there's any issues that are arising. And then the last one I'll talk about really is the RockSpot. The RockSpot is a different type of radar. So all the previous instruments I showed you can give you kind of an early warning that something's changing here and seeing these minor displacements happen. The RockSpot is kind of on the opposite end of the spectrum. It's a Doppler radar, and it can only measure fast-moving objects. This is more or less what the police are using to, radar detect you and give you tickets. Well, we're doing it to rocks. We're shooting these Doppler radar waves out there. We're measuring the shift over time, and we can see how fast the rocks are moving and where they're moving. So it doesn't stop the rocks from coming down, but it gives you nice statistics around how many rocks, how big are they, and where are they coming from. And this can be very useful when you have areas like a ramp that's right below a large section of high wall where you have consistent rockfall and you want to know what's your exposure in this area. Are my berms big enough? Are my controls good enough? This is a great tool for doing that. And also it can alert you when things are changing. Usually you don't have a lot of warning time if a rock falls from the time it detaches to the time it hits the road, but it does give you the opportunity to measure that and see how often and how much that's happening. So out of the monitoring radars, I just wanted to kind of summarize these. So we have the IBIS ArcSAR. This is our biggest type of radar that we use. It has a 360-degree field of view, so it can see all around it. It has a 5-kilometer range, so it sees out to 5 kilometers. And it does this 360-degree, 5-kilometer scan in about 60 seconds. So it's quite fast. Then kind of stepping down from that, I would go to the IBIS Evo. The only real difference between this IBIS Evo and the ArcSAR is the IBIS Evo only has about 80-degree field of view, so it doesn't see full 360. And sometimes that's all that's needed if you're sitting on a pit wall. You don't really need to see necessarily behind the mine anymore. You just need to see what's happening in the mine. So that's also quite common. The nice thing about the IBIS FM Evo as well is it's just a solar-powered unit, so it has required very low maintenance to maintain, just runs off of solar. And then we have our most targeted system, which is the Hydra X. We have one of these set up in the zone if you want to come check it out. This is a tripod unit that's just about this big. One person can carry it around. It has a shorter range of about 800 meters, and it only sees a 120-degree field of view. But it is higher resolution, so we consider it a more tactical monitoring system. When you have a known hazard, you might deploy a system like that to see in real time in this area that you're not covered by anything else, how fast is this landslide evolving. And then finally, as I mentioned before, we also quite often use the RockSpot, which is our Doppler type radar for tracking rock falls. All right, so I just want to show you some examples. What does this look like? I mean, a lot of times people ask me, what is this type of data? What does it actually do? Well, here's an example. This is a real example. This is from a mine in Arizona. And basically what you see here is this is a graph, and you have in inches. That's how you know it's in the US. And it goes from 0 to 50 inches on the vertical axis here. And then you can see the dates here. So this is back in November, and this is out in February. So this was the average of a group of pixels on a specific landslide above a working area. And this is what happened there. So we kind of start this. They have a steady trend. It's slightly regressive, but we'll call it steady, where there's movement occurring down here in the bottom corner. And then they had a blast, which is signified by this orange line here. So they blasted. And you see a very sharp acceleration, but it very quickly starts to decelerate. And that's why you see the curve of the line coming back in, if we all remember calculus. And then again, there's a blast. And again, this time it accelerates actually for a few days before it starts to decelerate in this case. And that's pretty concerning. But once it's once it hits that inflection point right around here and it starts to decelerate again, that's when they decide to go back in and start mining underneath it. So the advantage here, of course, is they can see what's happening in real time and how that landslide is evolving, and they can determine, is it safe to go back in there and start mining, and exactly when can we start doing that, which of course is very helpful for production needs. Not to mention the fact that you get to also go to your blasting crew and help them understand why their blast is making this thing accelerate so much. And then you can see actually over a long period of time it decelerates. It moves several feet, but it decelerates. And then you have a little rain event that happens here. Rain often causes things in mines to move, for many of you that know that. And you have a slight acceleration and then a long regression. And this landslide never really failed into the mine. They could track this. They had very little down operations time because of this landslide that was occurring. And so because they have these monitoring in place, they can really tell, oh, this is a safe place to be, or no, we should go mine somewhere else for the next day and a half until this thing starts to decelerate. And that's really one of the main advantages of it. And we have thousands of examples of doing this from different scales. I'll point out, like in this case, well, actually, I'll go back to the first one. If you look at this case, what happens is this is in millimeters now. So they had 2 meters of movement, and this one did fail out actually here in June. And it moved 2 meters before it failed over several months. So over that time, we could see how fast it's accelerating. We could determine when that's actually going to happen. And then on the opposite ends, you have a much smaller, this is a very small landslide. And in this case, it accelerated over just a few days. So you get a lot of different types of things that happen in there. And then maybe the most extreme types of examples when you get down to the 300 square meter size. This just evolved over the course of about 8 hours, and it only had about 10 millimeters of movement before it failed in that 8 hours. So we're kind of approaching rockfall in that scenario. And keep going, another 180 square meter area. This one failed in the course of, again, maybe you can say 8 hours or 12 hours, kind of depends how you pick the start. But a very small area, and it only moved about 20 millimeters before it failed. And another much larger one, so this one is interesting because we turned the radar on and immediately we see a landslide, and of course it's accelerating very quickly, and the next day it failed. So we have lots of examples like that. So the last one I'll show you is a very large 28,000 square meter area that failed, and in this case, in this top graph, what you see, I actually plot the inverse velocity, which is just 1 divided by the velocity. And the nice thing about doing that, it's a nice visual trick, because if you divide 1 by the velocity, if the velocity is infinity, that means that value turns to 0. So we can just kind of determine, basically fitting a line to this, well, roughly when will that hit 0? Because if it continues to accelerate at the same rate, we expect that line to be quite accurate in determining when the failure will actually happen. And I can show you more examples of that, but the main basis of that is it gives users the ability to determine when a failure will happen at these acceleration rates, so they know kind of when they can pull out and when they should be out of there before the failure actually happens, and they can track that in real time. Let's show you another example. This is what it looks like on the displacement maps. So this is what the users actually see along with these graphs. So here's the graphs that correspond to this failure zone here. And they can set alarms on this, right? So they can say, okay, if something moves more than, let's say, 2 inches per hour, alert us and send us an email about it. And in this case, they had a red alarm 18 hours before the failure, and they had the yellow alarm 44 hours before the failure. And this was a 3-bench failure covering about 3,600 square meters. And you can see quite clearly, okay, nothing happening on the displacement. This is the displacement here, so nothing happening for November. Coming into December, you see a slight change right here, and then a rapid acceleration, right? Pretty easy to see, I think. And you can see that this is the velocity graph here, so it's just taking the displacement over time. And you can see the velocity is quite stable. You see that little bump where it starts, and then of course it accelerates rapidly and fails here. And that's kind of what the users look at, so not so hard, but now I'll show you a very zoomed in view of that same exact data here. So this is the same data, and I'm looking for that tiny little bump in acceleration that happens 44 hours before the actual event occurs. And when you look at it, you can see the scale that we're dealing with here. We're dealing with, sub-millimeter displacements occurring, and the inflection point is really right here. And in this case, this is an evaluation of noise levels versus alarm states. And we can see, okay, we can go with the customer and we can optimize what are your best alarms that you can be using so that you're notified basically as soon as possible when some sort of acceleration happens on your slope, where that's happening and when that's happening. And then you can start to model exactly, let's say, when that could fail. And you can plan around that way. And it's quite useful. This is what it looks like in the map view. So this is a failure that happened actually in December of 2021. So what you're going to see and what you look at is a 30-minute time window here. So right now it's from 11:01 to 11:31. And then colors here that correspond to inches per day. So if it moves more than 3 inches per day in that 30-minute window, it's going to be red. This was during a very active period of rain and excitement. And you can see this is just going to step forward in time and go, oh, it's kind of, there's a lot of speckle. I don't really quite see much, but you'll start to notice something show up here. And it becomes more and more obvious as we go through the day. And you say, okay, that's a little more different than what we're typically seeing. And then about at 2:15 it failed, which is right about there. So it's quite easy for a user to pick out and understand exactly what's happening there. I mean, I think everybody in this room saw the giant purple dot show up, and yeah, that's a landslide that's happening. And at that point, it was moving more than 20 inches per day, and then at some point it's moving so fast the radar loses coherence, and it's just in an active boulders rolling down the hill type of state. All right, so then we'll kind of jump over to the rock spot, because what I showed you is stuff that can only measure up to a certain rate, and that's nice because you can see what's going to happen, you can plan around it. So then we thought, okay, well, we will really want to measure also what's happening during some sort of rockfall or event or failure, and that's where the Doppler radars come in. We made a new software to manage this because it's a completely different type of data set, and that software is called GeoCloud. We like to think of the rock spot as like somebody watching the slope with their eyes. You probably have seen in a mine where you might put somebody to watch, oh, this is a dangerous area. Let's watch it and just track how many type of rocks we see going and make sure our controls in place, such as berms and barriers, are working. What the problem with that, of course, is the human element of having somebody sit there and watch that. So the rock spot is really a machine version of that. It works day or night, it works in rain or snow. We're going to see rock falls that happen, and we plot these on 3D maps so the users can see it. It has a built-in camera, so we can overlay that data with the camera as well. So what does that look like? I mean, really what it comes down to in this case is statistics. So because we can't stop the rocks with the radar at any point, what we can do is collect statistics about where these rock falls are happening, how often they're happening, how big they are, and how fast they're moving, and what their travel paths are. And this can be really useful from the safety perspective when we're trying to keep people safe in the mine. So when it comes to the risk management of this data set, well, it's a lot of events that happen. So we also need to be able to manage all these types of rockfall events, plot them properly, put them in the right bin, say, okay, these are this size of rocks. We want to see all the events that happen when they're greater than 2 meters in size. We want to see all the events that happen when they're 1 to 2 meters in size, and stuff like that. So we really tailored it for the users so they can view these events. They can click on an event. They can see the camera image of the event and the video record, and then they can see the rockfall plot in the data as well. So I'll show you kind of a live example of what that looks like. So you'll see, it's so crazy because you hardly can see it with your eyes, but you'll see the rocks start come down here, and you'll also see them plot on here. I'll show it to you again. And this is the type of stuff that we see. So it tracks pretty small rocks down to the size of about 1 meter. So if you can imagine in many mine sites, that happens a lot. So you definitely need to have filters and determine what you really want to see and things like that. But yeah, it really covers the whole spectrum. So we're seeing very slow displacements occurring at the beginning of a lot of these events, and then we're also seeing very fast rockfall brittle events that are occurring too. All right, so what's in our portfolio? So how do we kind of put this all together? So we have different softwares for a lot of these different things, but it all is going to be brought together in our geotech data aggregation platform, which is Hexagon GeoMonitoring Hub. So we have in our slope monitoring, we have the instruments that are collecting and analyzing the data, and then they're actually sending that to the GeoMonitoring Hub where the users can interface with it, see the data, click on graphs, see what's happening there. Then from the safety side, we provide the rockfall management system, and that's through GeoCloud. And then finally, our newest release, we're actually using artificial intelligence through a process called AIDA to detect movements before the users will actually see them in the software as well. So one of the things we realize, of course, is we rely on our services or people or users to detect what's changing on the slope. But we have enough huge data sets that we could start training machine learning algorithms to pick those out for the users and to alert the users through a list, say, hey, these are the different areas that we detect are moving as well. So we continue to evolve in that, and that will continue to improve as well. It's looking very promising. And that really will just save time for the geotechnical staff so that they just get the data that they need and can make decisions quickly, which is often needed when you're dealing with landslides. The main software that processes and alerts on the radar data is called Guardian. So I'm just going to talk a little bit about that. This software has been developed for more than 15 years now. And the big thing behind this software is it needs to manage a lot of data. I mean, each radar is refreshing 200,000+ points every minute. So it's just a lot of data to handle. And it needs to digest that and give it that and put it in a format that other software can take that in. But the users often are interfacing with this Guardian data. The Guardian can take multiple radar data at once. So usually a mine site just has one big interface like this, and it just shows all the radar data despite how many radars they have and where they are in the mine. And that's quite useful for them because most users don't really need to play with the hardware or understand what's happening there. What they really want to see is the displacement data in real time for decision making. All the outputs are georeferenced, so also from a radar, every single point out there has an XYZ. That makes it easy to move back and forth between other softwares, and it also helps users understand exactly what their boundaries are for failures. You can import all sorts of different layers into this, as you can see in the image. You can put your geology in here, you can put faults in there, and it's really just meant to help you understand what's controlling these landslides and what different things and measures can we take. Can we dewater it? Can we put some weight on the toe? Can we take some weight off the top? These types of things. All right. So key features in there, I mean, a big part of it comes down to these graphs here, right? So it's nice to always see the images, the color bar of what's happening there, that's great. But it doesn't really tell you when it's gonna fail or how close you are to that. And that's why we just often are just showing a lot of graphs of different areas. Like you can see this blue one here. Anybody who's looking at that might say, oh yeah, it's continuing to accelerate. That's not a good thing. Whereas other times you might just have a very slow change that's happening. Okay, we call that yellow light. Okay, watch it, but probably it won't fail soon. And then of course you can have some very rapid accelerations like you see here. So it's you gotta kind of know your rocks, you kind of know geology, the geometry of your mine, the structural controls that are in place, and that's why we give these tools to the geotechs so they can put those pieces together and make fast decisions. Regarding that, really what it comes down to, it's not like somebody's gonna watch this computer 24/7. So a lot of times what happens is you just set limits. So you just set thresholds. You say, hey, if something's moving more than 2 millimeters a day, send me an email, show me a picture of what that area is. And you can get that delivered to your phone. And so a lot of times a geotech could be maybe going to bed at night and see, oh man, this area is accelerating. I better call the on-call and let them know that, not to work in that area. So a lot of stuff like that happens. And there's a lot of different notification methods, but probably email is the most common that people use nowadays that we all have smartphones. And then I'll bring up another topic that's really interesting that we work on, and that's what we call Guardian slow movement. And what you see here is a real-time project and a slow movement project. And it's the exact same data, actually. And if you're keen, you'll see that this shape of this landslide here kind of fits actually right in here. So what's happening is with radar data is we're always comparing results to the past. So it doesn't measure like a laser, like the true distance and measure that changed 1 centimeter. It measures change very accurately. So it can see that change in the sub-millimeter scale. But that change is just compared to a previous scan. So in the slow movement case, what we do is we actually compare, instead of to the previous scan, we compare it to a scan from yesterday. So if we look 24 hours ago, how did this scan change from 24 hours ago? And that reduces our baseline considerably. So we can see things that are moving very slowly in that case. And when we look at very large scale landslides, so maybe 10 benches or more, those typically evolve over several months. And if you can see that they're changing very slowly right when you cut the pit wall, you might implement some sort of dewatering or some other implementation to keep that thing from accelerating into the pit and failing. And that's really the point of slow movement. And it's something that's expanded a lot. So we did this like in the past with some very large scale mine, let's say failures that have occurred. And since then it's kind of been wildfire, like people realize, oh, this is actually very useful for understanding what can I do about this and having many months of warning before something actually occurs. So maybe you can't do anything, but at least you can plan your operations around the fact that if this accelerates, it's gonna fail. And this also is true on tailings. So you can see here, this is like a little dam, and we can see very small changes. So this is over the course of 4 months, and we don't even see, 10 millimeters of movement over 4 months. So we can say in this case, it's a very stable scenario, which also is nice to know. So maybe you're uncertain about what's happening in the area. Maybe somebody's reported some raveling or some events, or maybe you found some cracks. You might want to know, is this stable or not? Well, the radar is a good tool to tell you that because it can tell you that with a very high level of accuracy. All right, so that brings me to the services side of this. So there's a lot of things that I explained through that, kind of gloss over in some sense that the users have to know, and the training that goes behind that, and the support for the end users for this type of stuff, because many of it maybe they've never seen before. So we do offer support with every radar. I mean, currently pretty much every radar we have has some sort of support attached to that for the end user. And we also have 24/7 assisted services. So some sites will also just purchase our services so that we can maintain and monitor their data for them and set some sort of guidelines around what we do and how we communicate through their trigger action response plan. And we work together with a lot of mine sites on developing that and coming together with, okay, what's the best way to keep people safe and manage this data and keep people out of the hazardous zones? And that's what we do. So I just want to give you a little sample of that from one of our partners. Yeah, it includes a lot of different things. So again, that 24/7 monitoring service. We also do reporting. So sometimes some companies just want like a weekly or monthly report about what the data is doing just for the record keeping. We offer that slow movement analysis and advanced training. And then of course we make recommendations on the configurations and things that they should do there. So I want to give you an example. This is from one of our partners, Pueblo Viejo Mine in the Dominican Republic. Yeah, so they purchased the 24/7 monitoring services, so they want us to notify them of any areas that we see that are accelerating. We have a team based in Brazil that just works in a shift watching the status set and notifying them of anything that happens. So this is kind of an example of what that looks like. So here we see the graph. This graph associates to an area that's right around in here, and this is what happens over time. You can see there's some displacement occurring. Yeah, it's interesting, okay. Doesn't look like a rapid acceleration, but let's see. So we'll just mark that as the event start, and that's on January 15th, okay? Then we step forward a little bit, and we see that, okay, it's continuing in that same direction. Our Hexagon 24/7 team sent a report to the site saying, hey, we detect that there's something could be happening here, kind of yellow light situation. Okay, if you don't have to put the shovel right below it, maybe don't put the shovel right below it for now. But I wouldn't say it's critical yet. It kind of had a bit of an acceleration around 1 a.m. So we send a second report as per our guidelines with them. Just a flash report. It's basically just a screenshot with a note saying, this is where that area is. This is the movement rate that it's at right now compared to the last 24 hours. And then we step forward a little bit more. We had a slight regression, and then it continued again. We sent a third report, basically around noon, saying, this is kind of continuing. We get slight increase. You might notice there's a slightly steeper line here than it was back here. So we know we're a little bit higher velocity at this point. And then we actually trigger an alarm just 45 minutes later. So right around here, it hit our alarm threshold level, and it continued to accelerate past 4 p.m. Second red alarm was hit, and the failure happened at 5:40. And you can see that, back up, not that one yet. And you can see it's pretty small. Like there's not a lot of activity in that area. And the reason that many sites will use our services is because when you get very used to looking at this data and when you get really used to picking out what the zones of concern are, you also get really good at noticing these changes that are occurring. And so they are professionals in looking at this data. And in this case, it was quite successful. And we have hundreds of these successful cases. It happens every week in certain mines where they have a lot of activity. To bring you to a different scale, this is one from last year in October, so not too long ago. And what do we see? So this is a video, and what this video shows is, again, it's a 1 hour time window, a 1 day time window, and it's just the displacement of this area itself. And you can't really see a lot without going to the graph, but what I can tell you is it's consistently moving at a pretty high rate. And you can see, of course, it's 1, 2, 3, 4, 5, about 8 benches in height, so it's a pretty large feature that's occurring. So what does that look like? Well, here's an example of the flash report that gets sent for that. We have a camera attached to the radar, so we can send a picture of what that looks like, what the picture is, and then just a little note about what's happening there. Okay, and then what you see here is the inverse velocity chart. And this is very commonly used because what you'll see is they all kind of point to the same spot out in space here. And that's our failure time. So ahead of time we can know, okay, at this current rate, we expect it to fail at this time. And we can set alarms on that time too. We can say, hey, if that's gonna happen in the next 12 hours, send me an alert. If it's not gonna happen in the next 12 hours, I'm okay with just continuing as is until the next shift, sort of stuff. So there's a video of what that event looks like when it actually does fail. So you see in real time. And yeah, it was almost at midnight actually, so it's the middle of the night, so you can just see it with the infrared camera there. But yeah, it was a pretty nice event. The site knew that it was happening. Of course, you don't see any equipment chilling out below here because, yeah, they're very aware that that's about to happen. Yeah, all right. So these assisted monitoring services and benefits, I mean, it really is continuous data checks night and day. So they're always, you know, with many sites, what we say is the SOP is maybe check the data every 45 minutes, something like that. Check to see if you have any accelerations that are occurring, and then just notify them if you see anything happening. A big part of this is integrating that into the mine process. So, okay, let's say we trigger an alarm. Okay, now what do we do, right? And then what does the mine do when they get that alarm? So we really have to work with them together on optimizing that. It usually takes some time to optimize that and fit together because every mine kind of has a different trigger action response plan when it comes to dealing with these types of things. And that's also evolved over the course of the years because since radar monitoring has become so much more popular, the ability to track and monitor these things has also increased greatly. And it's given people a lot better tools to understand how their pit walls are changing. So how does this work really? Well, you know, we have all these sensors that are out there collecting this data, and most mines have their own geotechnical team, like in PV's case. We just kind of add an extra layer of check, right? It saves them a lot of time and bring that expertise of looking at these types of data sets and determining what's gonna happen. And we bring that to the geotech team and integrate it into their TARP process. So they have their own TARP, so they have other triggers that can happen, but we also have a trigger, which is that if we see an area accelerating, we're gonna trigger that TARP and tell them, hey, this is a big area of concern. So what does that look like? Well, we have our green, kind of yellow, really yellow, and then red. And this really just describes the different states that we can be at. Of course, a progressive or accelerating deformation puts you immediately in threat level 4. For example, if you don't have data availability or a person available for a 30-minute window, that can put you in a red state. You know, if you can make a phone call and you're not able to connect as through the escalation protocol, that can put you in a red state. So we kind of put together these type of matrix of different things that can occur to trigger the response that's needed. And really what that comes down to is making sure that no operators or people in the mine themselves can be impacted by any of these things. And then it comes down to technical support. Okay, sure, we also need to maintain all this stuff. We're the experts in maintaining all this stuff. We want to bring it, basically We want to, make sure that things are always running. You never really want to have your monitoring system for safety go down. So we have more than 15 now. We have 20 technical support centers in the world. And really they're just around the places where you expect a lot of mines, like, the Western US or South Africa or Australia, these types of places. Our headquarters is in Pisa, Italy. So it's kind of where everything comes out. And we have 60 people, mostly geologists and engineers, that are working on this project. This kind of overlay of where it is, where all the different places are. We're here, so yeah, all over the world pretty much that we're working on this stuff. All right, well, thank you for your time.